The cross product is an operation that takes two vectors and it produces a third vector that is orthogonal or perpendicular to both given. This is also known as the vector product. The cross product is mostly used in finding torque from classical physics as well as in electromagnetics when it comes to finding electric or magnetic fields. Alright, so this is A cross B. The order does matter. If you were to switch the order around and have B cross A, you would find a different answer, and we will talk about those properties later. The equation is A cross B equals the magnitude of A times the magnitude of B times the sine of theta times n. So as we discussed before, when we see vectors in absolute value, this means that these are the magnitude of the vectors, and magnitudes are given in a scalar value. Theta is the angle between vectors A and B, and then n is the normal unit vector. Again, normal, perpendicular, and orthogonal mean the same thing. N just gives the direction. The magnitude is given with the AV sine theta. So the first part is going to be a scalar, and then this is your vector. So remember that when we have one vector, it corresponds to a line. If we have two vectors, and they are not parallel to each other, then we have a plane. So n is the unit vector that is perpendicular to the plane. So here are some properties of the cross product. As said from before, the order matters because this is not commutative. As a matter of fact, this is anti-commutative, which means A cross B equals the negative of B cross A. The second property of this is that it is distributive over addition. Vector A cross the sum of vectors B and C is equal to A cross B plus A cross C. And also A plus B cross C is equal to A cross C plus B cross C. And then the third property, if A cross B equals 0, this means A and B are parallel. So if you remember from the dot product, whenever A dot B equals 0, that means vectors A and B are perpendicular. However, for the cross product, if A cross B is 0, or B cross A equals 0, then that means vectors A and B are parallel. Okay, so let's talk about how to calculate the cross product. If we have two vectors, A equals AX, AY, AZ, and B equals BX, BY, BZ, and we want to find A cross B, we would use a determinant. So recall that in vector notation, we have components I, J, and K, with I representing the X components, J representing the Y components, and K representing the Z components. Vector A would go into the second row, so we have AX, AY, AZ, and then BX, BY, BZ in the last row since B is the second vector. So to calculate a 3x3 determinant, we would usually choose a row to go across or a column to go across. Usually when it comes to I, J, K components, we would choose the top row, going from left to right. And then since we've chosen the top row, we would have I, J, and K be scalars of each 2x2 determinant. Now, when solving 3x3 determinants, there is a pattern where it's plus, minus, plus, minus, plus, minus, plus, minus, plus. So since we're choosing the top row, it's plus minus plus. So this means that the j would have a minus sign right here. So now we can start the process. We're starting with I. We would cross out this column, and then we would have AY, AZ, BY, and BZ. After we're finished with I, we would go to J. Crossing the middle column out, we would have AX, AZ, BX, and BZ. After we finish the J column, we'd go to the K column, and we put in AX, AY, BX, and BY. Okay, so to calculate a 2 by 2 determinant, we take this diagonal, we multiply these, and we subtract it with the product of the other diagonal. So in this case, A cross B equals AY times BZ minus AZ times BY, and this is scaled by I, minus AX times BZ minus AZ times BX. This is component for J, and then plus AX times BY minus AY times BX. This is K. So let's do an example. Find A cross B and B cross A given that A equals 1, 2, 2 and B equals 2, 5, negative 1. So we'll start with A cross B, and we're going to do our 3 by 3 determinant. A is their first vector, so we put that in the second column, second row, and we put B in the third row. So again, we cross out the ijk row, and then we take turns going across each column. So we'll start with I. This is 2 times negative 1 minus 2 times 5. And then we alternate the sign for j. Cross this column out. We have 1 times negative 1 minus 2 times 2. Then we alternate the signs for plus again for k. Crossing this column out, we have 1 times 5 minus 2 times 2. So we can say that A cross B equals, I'm going to write in component form, negative 12, 5, 1. Now let's do B cross A. So this time, since the order of A and B switched, B is now our first vector, so we put 2, 5, negative 1 in the second row now. And then for ijk, we'll start with I. 5 times 2 minus negative 1 times 2. And we alternate for the minus for j. 2 times 2 minus negative 1 times 1 plus. And then for k we have 2 times 2 minus 5 times 1. And then B cross A equals 12, negative 5, negative 1. If you notice, this is just the vector of A cross B in the other direction, because this is from the anti-commutative property from earlier. So remember, A cross B equals negative B cross A. So let's take a look at the figure below. We have vector A in green and we have vector B in blue, and the tails of them are joined at a single point. And with these two vectors, we can create a parallelogram if we make a copy of vector B and attach its tail to the head of vector A, and if we make a copy of vector A and we attach its tail to the head of vector B. Okay, and the area of a parallelogram in terms of vectors can be found by just taking the magnitude of the cross product. Now remember from the formula from earlier that A cross B equals the magnitude of A times the magnitude of B times sine theta times n. So taking the magnitude of A cross B. We're going to do the same on the other side. However, remember the n, that's a normal unit vector, so it has a magnitude of 1, so we don't need to include it in this equation. And then sine of theta, that is already in a scalar, so we don't need the bars around those. So the magnitude of A cross B is just equal to the magnitude of A times the magnitude of B times sine theta. So to help visualize this equation, recall that the area of a parallelogram is its base times its height. B is the magnitude vector B, and the height h, that is found by dropping a line from the top of the parallelogram to its base so that it is perpendicular to it. So this dashed line is the height h. Now let's make an equation so that we have h expressed in terms of our known values. So what we have is a, theta, and h, and it forms a right triangle. We're going to use a trig function to make that relation. So we have sine of theta, and remember that the sine of theta is equal to the opposite side over the hypotenuse, and then the opposite side is h, and then the hypotenuse is the magnitude of a. So rearranging this equation, we have h equals the magnitude of a times sine theta. So that's how we get the area equals the product of the magnitude of both vectors times sine theta, which is the angle between them. Okay, so let's do example 2. Points A, negative 1, 0, 1, B, 0, 3, 3, and C, 1, 1, negative 2, make up a triangle. Find a vector orthogonal to the triangle, and what is the area of the triangle? So we can choose any point we want. Let's say we choose point A, right? Point A is connected to two sides of the triangle, and those two sides we can make vectors AB and vectors AC, since they share the same initial point A. So AB equals, remember to find vector AB, we do the final, which is B, minus the initial A. We subtract each component. So 0 minus negative 1 gives us 1, 3 minus 0 gives us a 3, and 3 minus 1 gives us a 2. And then for AC, we do the same, with the final being the point C now. This gives us 2, 1, and negative 3. Now remember that an area of a triangle equals half the base times its height. So remember that the area is the cross product of two vectors, and this time we need to add a half, multiply by half. So let's do the cross product. AB cross AC. We're going to make the determinant ijk 1, 3, 2, and 2, 1, negative 3. We're going to go across ijk, and then we're going to cross the I column, the j column, and the k column. So we'll start with I, taking this diagonal and subtracting it with the other diagonal. So it's 3 times 3, subtracted by 2 times 1. And then for j, 1 times negative 3 minus 2 times 2. And now for the k, 1 times 1 minus 3 times 2. And then remember, because this is a 3 by 3 determinant, whenever we have the middle value, j, that is going to have a negative sign in front of the answer. So this equals a 9 minus 2, negative 3, minus 4, 1 minus 6. So AB cross AC equals negative 11, 7, negative 5. So this is the vector that is going to be orthogonal to the triangle created by A, B, and C. Now, just a note, you can switch the order around, and yes, this can be scaled by a -1. So 11, -7, and 5 is also a vector that is orthogonal to the triangle. It's just pointing in the other direction. Now for part B, the area of the triangle is just going to be 1/2 times the magnitude of AB cross AC. And then the magnitude of AB cross AC equal to the square root of each component, the sum of each component squared. So the area of the triangle equals 195 divided by 2.